The limit comparison test. Objectives. By the end of this lesson, you should be able to use the limit comparison test to determine if a series converges or diverges. Alright, the limit comparison test. So suppose we have a sub n is greater than 0 and b sub n is greater than 0. So we have all positive terms for all n, or at least all n past some certain threshold capital N. So as long as we have positive terms past a certain point. If the limit as n approaches infinity of a sub n over b sub n exists and is both positive and finite, then the two different series, the series with general term a sub n and the series with general term b sub n, either both converge or they both diverge. So here's the informal version of the limit comparison test. So let's say we're given a series, the sum of a sub n. We choose another series, the sum of some other general term b sub n, that you already know either converges or diverges. Then we have to consider the limit as n approaches infinity of a sub n over b sub n. So we do the ratio of the two different general terms, a sub n over b sub n. And if this limit converges to any number L that is a positive and finite number, then both of those series that we compared to each other have the exact same behavior. So let's go ahead and try to take a look at a few examples where we're going to try the limit comparison test. Alright, so we want to apply the limit comparison test to each of the following series. So here I have the sum from n equals 1 to infinity of 1 over 3 to the n minus 1. And this should look familiar because we attempted to use the direct comparison test on this series earlier, and the direct comparison test gave us an inconclusive result. So we did attempt to compare this series to 1 over 3 to the n using direct comparison, so let's try to use that same series, 1 over 3 to the n, and use the limit comparison test. So we have to look at the limit as n approaches infinity of 1 over 3 to the n minus 1 over 1 over 3 to the n. So we're comparing this series to the sum from n equals 1 to infinity of 1 over 3 to the n, which is really just 1 over 3 as a quantity to the n, and we know that this converges by the geometric series test since 1/3 is less than 1. So we're going to use this limit of the general terms. So here's our a sub n, here's our b sub n. And we want to see if this limit converges to a positive finite number. So now this is the limit as n approaches infinity of 1 over 3 to the n minus 1 times the reciprocal of the denominator, 3 to the n over 1. So this is 3 to the n over 3 to the n minus 1. And we have this limit as n approaches infinity. So now here, this limit at infinity, since we have 3 to the n over 3 to the n, it's just going to be the numbers that came in front, right, the 1 over 1, so this limit converges to 1. So that is a positive finite number. So by the limit comparison test, the original series is also going to converge. The two series that we compared their general terms are going to have the same behavior. So we picked a convergent series to compare it to, and since we got out a positive finite number, the limit of 1 over 3 to the n minus 1 is going to converge. So similar to the direct comparison test, we have to start out by just choosing some other series on our own, and we have to know whether that other series converges or diverges. Then we apply this limit, and if the limit is a positive finite number as an answer, then the two series behave the same way. Alright, so now I have the sum from n equals 1 to infinity of 2n squared plus 2n minus 1 over n to the 5 over 2 minus 3n plus 8. Now these particular series lend themselves really well to the limit comparison test, and it's just a matter of recognizing that we should use the limit comparison test on this type of problem And there is a general way to decide what you're going to compare this particular type of infinite series to. So the series we're actually going to compare it to is the sum from n equals 1 to infinity of 1 over n to the 1/2. And let's talk about how I got that. So in the denominator here, I have n to the 5 over 2 being the dominating term, and in the numerator, I have 2n squared being the dominating term. So I'm choosing to compare it to this p series, 1 over n to the 1/2, as that is the difference between these exponents. So 2 and this is 2.5, so the difference between those is 1/2. And I want to compare it to this p series because I know that this p series diverges because 1/2 is less than 1. And you're going to see how this is nicely going to work out when I set up the limit required. So I'm going to do the limit as n approaches infinity so I have 2n squared plus 2n minus 1 over n to the 5 over 2 minus 3n plus 8 over this general term of the series I just chose, 1 over n to the 1/2. So now when I multiply by the reciprocal, this is the limit as n approaches infinity. So I have 2n squared plus 2n minus 1 over n to the 5 over 2 minus 3n plus 8 times, I have that n to the 1/2 moves to the numerator over 1 when I multiply by the reciprocal. And so these are being multiplied here. So the dominating term in the bottom is still n to the 5/2, and I'm thinking about this limit as n approaches infinity. So now, if I were to multiply this all out, although I don't really have to, this n to the 1/2 would multiply by the 2n squared, and those exponents, 2 and 1/2, would add together. So if I distributed in the n to the 1/2, I'd get 2n to the 5 over 2. And then I can keep going if I want, even though I don't need to, but I would get 2n to the 3 over 2 minus n to the 1 over 2. So now, in the numerator, the dominating term is 2n to the 5 over 2. So the exponents now in the numerator and denominator, or the degrees, I should say, match. So the leading coefficient is 2 over 1, so this limit equals 2, which is positive and finite. So by the limit comparison test, these two infinite series have the same behavior. So the sum of 2n squared plus 2n minus 1 over n to the 5/2 minus 3n plus 8 also diverges. So we did make sure to include that the series we compared it to, why it diverged. We showed our work for the limit comparison test. Since we got a positive finite number, we know that the two infinite series behave the same way. They both diverge. Alright, this next one, the sum from n equals 2 to infinity of n squared minus 1 over n cubed. So again, just to talk about the starting index here, we had to start at an index of 2 so that when I plug into 2 squared is 4 minus 1 is going to give me out a value that is positive, right? So I'm going to get 4 minus 1, which is 3. If I start out with the index of 1, then I'm going to get 1 squared minus 1, which is 0, and 0 is not positive or negative. So I want to start out with all positive terms. So in the previous two examples, just to clarify, we would want to think about whether or not those are going to yield positive terms past a particular value. So here, because we have all positive terms, we can apply the limit comparison test. So we do want to make that check for ourselves before we attempt to use the test. And so now it's a matter of, well, what do I compare this particular series to? So because here I have n squared minus 1 over n cubed, I'm going to go ahead and compare this to the sum from n equals 2 to infinity of 1 over n. So the highest power up here was 2, this one was 3, so the difference between the two is 1. And this turns out to be harmonic, so this thing diverges. So now we're going to go ahead and set up our limit. So the limit as n approaches infinity of n squared minus 1 over n cubed. So it would technically be over 1 over n, but that's times n over 1. So I'm skipping that step and just jumping to multiplying by the reciprocal. So now this is the limit as n approaches infinity. Well, this is multiplication across the numerator, so that's n cubed minus n over n cubed. This limit goes to 1, because now the degrees match. So this is positive and finite. So I've satisfied the limit comparison test. So by the limit comparison test, we know that the original series is going to behave the same way as the harmonic series. It too is going to diverge. And now just to go over one final example. So the sum from n equals 1 to infinity of n cubed minus n over n to the fifth minus 1. So hopefully you can kind of see the pattern here. I have on this one I have two different polynomials over each other, so I have a rational function. So what I'm looking at is to find the difference in the degrees and use that as a way to decide what series to compare it to. So it's a p series with p being 2, the difference between 3 and 5, and that's going to work when the degree in the denominator is bigger. So I'm going to have n equals 1 to infinity of 1 over n squared is what I'm comparing it to. Since 2 is greater than 1, this p-series converges. And now we'll set up our limit as n approaches infinity of n cubed minus n over n to the fifth minus 1 times, I'm going to do that multiplied by the reciprocal already, n squared over 1. So this is the limit as n approaches infinity of n to the fifth minus n cubed over n to the fifth minus 1. This limit at infinity converges to 1. So since this is positive and finite, both of these series behave the same way, so that must mean by the limit comparison test, the original series n cubed minus n over n to the fifth minus 1 must also converge. So just real quick, I'm going to go ahead and write down the reciprocal of this general term and talk about why the limit comparison test is unnecessary. So n to the fifth minus 1 over n cubed minus n. So, you know, if you have started to see or get in the habit of noticing what a limit comparison test setup might start out as, this looks similar to it, but notice here I should just directly apply the nth term test. That's the first test I should apply no matter what anyways. So if I apply the nth term test here, just the limit as n approaches infinity of n to the fifth minus 1 over n cubed minus n, this limit goes to infinity, which is not 0. So by the nth term test, we have that this series diverges. So that's the first thing you should try no matter what. But you can see that if I tried the nth term test on this general term, then this would go to 0, which would mean the nth term test is inconclusive, so we'd have to try something else. So here, the key is that the denominator, or the degree of the denominator, would have to be bigger in order for us to use this trick of subtracting the numerator's degree from the denominator's degree to find our p-series that we're comparing it to.